Welcome to the New Calculus channel. My name is John Gabriel. So in the previous two videos on this topic of the 5 claims, I discussed claim 1 and claim 2. These claims are incorrectly called postulates or axioms by the infinitely stupid morons in mainstream academia. So let's just revise what claim 1 says. For those of you who don't know Greek, that word there says atimata, which means a claim or a requirement or something that needs to be in place. So the original definition from Euclid's Elements is given down here in the box at the bottom where it says itisto apopandos simiu epi pan simion ephian gramin aragin. So what that really means is that we know that any two paths have the same length if the points on one path lie evenly on the other, right? So as I explained in the previous video, if you have, let's say, a path like that or a path like this, then these points here lie evenly on each other, but it's not a straight line, okay? And we'll see what the difference is now in the following definition. It's only a straight line if there is no other distance that can lie evenly on it. In other words, it's a straight line if there is only one other distance with the points lying evenly on the line. And so there is only one path whose points do not lie evenly on any other equidistant line except itself, and that line is called a straight line. So it doesn't really matter what you do, okay? You can create a path like that, yes? And there will be another path that is equal to this, or innumerably many paths that are equal to this. There could be that path, and let's say another one if we did that or something, which is equal to it in this particular scheme here. And we can say, well, this particular path doesn't lie evenly on the other. That's a simple case. And also, as far as the first case I showed you, where I did this, and I said, okay, well, that path is the same as that, yes, and that means it can't be a straight line because this path here is only one of innumerably many paths that has the same distance as this entire path, okay? So you need to think about that a little bit, but the definition of a straight line is very clear and very simple in the Elements. It's not an axiom, it's not a postulate, as fools have been assuming over the past 200 to 300 years. Okay, let's revise the second one, and the second one states that you can extend the line in any direction. Well, this really follows from the first axiom, doesn't it? It follows from this one here. All you have to do is basically partition this line into two parts. They needn't be equal either. So to produce a line, to convince yourself that it can be produced in any direction, just partition that line anywhere along the line, and you can reason as follows. Well, had you created that path according to the first claim, then the second claim must be true because you can partition it in any point along this straight line. Okay, so the second one follows too. The third one and the fourth one are pretty simple. The third one states that you can draw a circle, and it also follows from the previous two because any circle can be drawn. What is a circle really? It's the boundary, this red boundary of any center in space. Now remember, while this here is a visualization of a circle, it's not strictly speaking a circle, okay? Because a circle has no width, no length, no breadth, nothing. This boundary here is just an imaginary set of points, or an imaginary path, okay? So this is a path on the circle, and you can create any size circle with any size radius. Incidentally, in the original Greek Elements, the word radius is not used. Okay, so if you go here and look at 3, the word used is diastimati. kiplon. Okay, and that means, let's read the whole thing. Ke pandi kendro ke diastimati kiplon grapheste. Okay, so kendro is center and space, circle. Okay, so diastimati is a polymorphic word, and it can mean space, it can mean radius, it can mean area, volume, anything. But in this context here, it obviously means the space of the circle, which is affected by the length of the radius. So we could really just rip that word out and put radius in there, and we won't lose the meaning of the third claim. So going back to this third claim, that's all it says, is that you can create any circle of any size, okay, and any radius given a particular center, which we've seen from the previous two claims. The fourth claim says that all right angles are equal to each other, and of course this is defined already in Book 1 in Definition 10. There is nothing to prove. If you had to draw a circle, the point at which the perpendicular lines meet is the center. So if these are the perpendicular lines, there's a center, and you can draw 4 equal angles, and they never change because the angle between these two lines remains the same. It doesn't matter how big or small the circle is, right? Okay, so this fourth claim says that right angles are equal to each other. It doesn't have to be proved because we've defined what are right angles. And now I'm going to reveal some new knowledge in the fifth one that you've never seen or heard of before, but this is being referred to as the fifth or parallel postulate for I don't know how many hundreds of years, and it kind of shows the lack of mathematical aptitude that most mainstream academics display, just wide open. They're infinitely stupid, beyond correction, and there is no way you can fix a mind that refuses to be corrected. So it says the interior angles on the same side of a transversal crossing two lines are both right angles if the lines are parallel. Well, I'm going to tell you something now, and pay attention carefully because you've never heard this in your entire life, not even by your teachers or your lecturers. Okay? You can draw any two lines. Let's say, oh, let me just draw proper lines. You can draw any two lines. Let's draw that line, and let's draw this line like that, okay? If you take a transversal like that, okay, and it doesn't matter how you move the transversal, like that or like that, these two angles, let me just draw here, the sum of these two angles here will always equal to the same value, just as the sum of these two angles will equal to the same value. So you can call this the fundamental Gabriel theorem of non-parallel lines, if you wish, okay? What I'm telling you, what I say, is that these two angles here always have the same sum, just as these two have. Right? Why is that? Well, it's pretty simple. You should be able to see the answer right away. Aren't these two angles part of a triangle here? Right? Yes, they are. Which means that since these angles here add up to 180 degrees, these two will always, added to this, imply that the sum of these two is equal to 180 degrees, is equal to the same value, because all we do is subtract that from 180 degrees and we get the third angle. So let's see how this works in terms of live interactive demo. Well, up here I've written the sum of these two cointerior angles. Now notice, it doesn't matter how you move the transversal, okay? It doesn't matter how. Those two angles, the sum of those two angles will remain the same. And in fact, they even remain the same if these two green lines don't meet. In other words, if they're parallel. And guess what? The fifth so-called postulate is very provable. Because if you look at this scheme here, this third angle plus the sum of these two angles adds up to 180 degrees, right? Therefore, the only time that the lines are parallel is if there isn't a third angle where I'm pointing to with a cross here. there's no third angle. So for example, if we had parallel lines like that, or almost parallel, I'm not going to get it exactly right, but you'll get the idea. So if they're parallel like that, then there is no third angle here, right? So, and these here would automatically add up to 180, just because these lines are not straight. So this is the Gabriel, the basic or most simple Gabriel theorem that you never learned at school, and that I'm revealing to you for the first time. Okay, chances are you're all incredible morons and will not get this the first time round. So I suggest that you watch this video several times until you're able to understand. And those are the 5 claims that were made by Euclid. They were not postulates or axioms. In fact, the word axiom doesn't appear anywhere in the ancient Greek, and the translation of the word etimata into postulates is completely wrong. Also, kimi, emia, means common meanings. That translation isn't too bad, but these here are sometimes also referred to as the axioms, also by ignoramuses. They're not axioms at all. Things that are equal to the same things are equal to one another. There's nothing to prove there. If I talk about the color red and think of something else that's red, it's also red because it's red. There's nothing to prove. Okay? So, just to finalize, what I wanted to say on this is that these here are referred to as the foundation of mathematics, and the ancient Greek would probably be laughing themselves to no end just to see what the academic morons of today have come up with and have never understood, and that axioms are not necessary in mathematics in any way, shape or form. Okay, and in the Greek word axiom doesn't really mean postulate, and it doesn't mean etimata, and it doesn't mean chimera and yeah. Okay, so it doesn't mean any of these. So you basically had morons teaching you mathematics for hundreds of years, and so it's unremarkable that you don't understand these things. If somebody who never understood them tries to explain them to you, it automatically follows, doesn't it? Okay, so now in this video you've learned a new theorem, the Gabriel theorem, which states that even if these lines are not parallel, the sum of the 2 angles on either side of the transversal is always the same. Okay, so remember that nice, neat little theorem, and it also helps you to prove. It helps you to prove the so-called unprovable axiom 5 or postulate 5. That academic morons can miss something this simple is not surprising to me. They've messed up mathematics in just about every way possible, beginning with the incorrigible and delusional nutcase George Cantor. So I hope you've enjoyed this video, and that you'll join me again in the next video for another exciting topic and some new knowledge also. I plan to talk about the formation of numbers, or the representation of numbers using radix systems. Right, so that's pretty much it. I'm a little out of breath right now. This is the New Calculus channel. I am John Gabriel. Till next time.